Well, good evening. I'm Charles Schultz, and this is the Randomizer. And tonight we're going to be talking about an interesting subject related to meteorology, aerology, which is more of a greater set of atmospheric conditions. And aerology includes, or I should say, usually focuses on the entire height or depth of the atmosphere, including everything, whereas meteorology generally seems to focus on the lower couple of miles closer to the ground. So the whole vertical extent of the atmosphere is fair game if you're studying aerology, and it has a long and venerable history. And the term itself isn't that old, but we'll talk all about that very shortly here. So go to SchultzLaboratories.com or UniverseScienceCenter.com, go to our pages, click through to the Randomizer every weekday at 6 p.m. Eastern Standard Time, and join us live with your questions, comments, and ideas. And you'll be on the show and be able to say what you wish, and we'll answer your questions the best we can. Also, our classes have started up again. Robotics is in session Mondays at 9 p.m. Eastern Standard Time. And if you have an opportunity to help see what we're about, put on your Oculus or your 3D headset and go to our site, the Universe Science Center or SchultzLaboratories.com, and explore our galleries and exhibits and play with the things. If you're homeschooling or just want to learn a different subject, come on in, have a look around at some of the stuff. We have computers and genetics and a lot of other stuff in there, planetary science, and we're going to be expanding it all the time. So, that being said, let's get on to the subject of aerology. So what is it all about? Now, we all know that people have studied the weather for quite some time, and the history of studying the weather really goes back to around 3000 BC. Records in India indicate that they already had classified many of the phenomena of weather, and including the formation of clouds, the movement of winds, the precipitation of rain, and also that they recognized that these seasonal changes that occurred were because of the Earth moving around the sun. So 5,000 years ago, they actually recognized that the Earth was not stationary in space in India, and many of their records show that, which is an interesting thing when you think about how long it took the rest of the classical world to reach that state. On the other hand, most of the effects that we experience due to weather occur really in the lower couple of miles of atmosphere. Some of the effects include hail, which is the precipitation freezing in ice pellets being carried back to altitude where it accretes more moisture and gets to be larger. And this cycle occurs many times until finally the updrafts cannot support the hail and it falls to the ground. Now, if you ever see hail and you split it open, you will see that there are concentric layers to it, just like a gumball. And this is because these accreted layers of water build up over each passage to altitude and back down again. So updrafts and downdrafts. But this really all happens very close to the surface of the Earth. And many times, if you've flown in an airplane and you're at an altitude of 30,000 feet or so, you recognize that just about all the clouds are way below you. This is interesting because this means all the precipitation that we're normally experiencing happens in these lower layers. So aerology actually focuses on many of the things that happen at higher altitudes. For instance, at very high altitudes, some clouds actually contain crystals of nitric acid in Earth's atmosphere. What an amazing thing to discover. And you know, the real study of aerology didn't occur until much later in our history. Because we didn't have the technology to reach those upper levels, except if you were on a mountainside. And there, of course, there are other things that step in. Proximity to the ground, the mountain's bulk itself to the air has a lot to do with the effects that you observe. So now let's think about it. Meteorology, you know, they often will use satellites these days to look at the movement of cloud masses. And that could be done from the ground to some degree, but predictions have been notoriously difficult to do without some of the understanding of cells of temperature and moving air. If we look at who really studied the air and its effects and structure over the centuries, we discover that, for instance, David Rutherford. Rutherford was a British chemist born in 1745. In 1772, he discovered nitrogen gas and what it was, and understood that it was a large component of our atmosphere. We didn't even know that. And it took a lot of time for people to figure out literally what our air is made of. If you go and you look it up on any table, you'll find that it's like 21% oxygen roughly, about 70%, 78% nitrogen, and then what's the rest of it? Well, there's about 1.3% of argon gas, and it's inert and it doesn't react chemically with anything under normal circumstances. And that's pretty much the whole atmosphere. When you hear about carbon dioxide or other gases and methane, you're talking extremely tiny fractions of a percent here and there. 0.3% would be an awful lot. And so when we're looking at the percentages of gases in our atmosphere, the bulk of it is nitrogen, 78%, 21% oxygen, 20.9 to 20.6, depending on where you are usually. And separating those gases out was very difficult, and the study of it was hard to do. It wasn't really until Antoine Lavoisier, the French chemist, and he worked on oxygen. He named it, he studied its effects, and it was 1772 when he understood what a large part of the atmosphere that it was. So when you put together the work of Rutherford and Lavoisier, these are the two fellows who understood the bulk of what our atmosphere is. But what about the moisture and the effects of weather? Well, studies of cloud formation go back a long time. 600 BC, Thales, the Greek, made the first seasonal crop forecasts. And what he did is he kept records of how the seasons proceeded and the effects leading up to them. And he looked for trends, and he started telling people it's most likely your crops are going to do well unless, or you understand, he got into the prediction business. And so, 600 BC, that's quite a while back, 2,600 years ago. If you start looking at Democritus, the same fellow who espoused atomic theory around 400 BC, he also began studying weather and making predictions, and he also tried to convince people not only could he predict the weather, but other things as well, which, okay, that's kind of a sneaky thing to do, but he was successful enough in his weather predictions that people actually trusted a lot of his predictions. And there was also pretty good evidence that Hippocrates around the time was quite involved in the study. He actually wrote a treatise called Airs, Water, and Places, and he talked about the effects of climate and water and atmosphere and precipitation. So this is an old study, but the word explaining aerology didn't show up until the literature showed evidence of it between 1745 and 1755. So as a term, it's less than 300 years old, about 250, 260 years old. So the term was meant to study not just our weather, but everything above it. So now let's talk about that. It wasn't really until the Montgolfier brothers invented the hot air balloon, their aerostat, and this was around 1782 that they got the first one to fly, and the first person went up in a hot air balloon in 1783 due to the Montgolfier brothers. Well, one of the things they did was they sent animals like a chicken and a goat and a pig up to high altitudes and brought them back down, and in some cases found that they had died of hypoxia. So they understood that at a certain altitude that the air was so thin that you would expire. Now this was actually expected because there were mountain explorers who climbed mountains all over the world and understood that the higher you went, the lower the air pressure was and the thinner the air was, and it was harder to breathe. So it wasn't a surprise, but they were actually able to gauge at what altitude you were likely to die from a lack of oxygen. So this was one of the first studies of the effects above our traditional reach in the atmosphere. And later, the studies depended on airplanes and balloons for the most part. So a lot of aerology was done by high altitude studies using advanced technologies, high flight vehicles and balloons. Now, one of the most interesting things we found is all about lightning. Lightning is actually one of the most important forces in our weather. And it basically happens because during the formation of clouds, The movement of air is known to generate static charges. Dry air is very good at it. Ice cold air, because the moisture freezes, is also very good at it. And so, studying these effects, we find charges build and build to the point where there literally is an arc through the atmosphere and a discharge of that static spark occurs. You've walked across a carpet and picked up a charge and reached for a doorknob and heard a snap and been shocked. Well, you've built up a charge, and when your finger got close to that doorknob, random charges of the atmosphere allowed the insulation to puncture. And once it punctures, the air itself becomes a conductive medium. It's ionized. And so the electric current can then flow, and that's where the spark comes from. On the scale of our atmosphere, cosmic rays from space are literally the things that create the charged ionized pathways in our air. And the lightning strokes follow those. And in doing so, they combust the nitrogen. They burn it with the oxygen and create nitric acid when it combines with the moisture present in the air. Now, at very high altitudes, this can create crystals of nitric acid in some of the clouds. And these are at altitudes above 7 miles, 10 miles. You may have heard of noctilucent clouds. When the sun is down, there are these faint, pearly, rainbowish clouds at the very, very high altitudes. They're almost always ice crystals or maybe even crystals of frozen nitric acid. Now, these are crystals that are so high above the atmosphere that when the sun sets, the limb of the earth isn't blocking all of the light. You're down here in the shadow on the curve of the earth, but the sun is still shining up through the higher atmosphere. And that's when noctilucent clouds begin to show. Lately, the most important discoveries have been by the space shuttle a few years back and by the International Space Station. They have discovered an amazing thing happens when lightning strokes flow through our atmosphere. Think about this. Lightning is many tens of millions of volts and hundreds of millions of amps in many cases. The energy in it is incredible. It is greater energy than just about any particle accelerator we've ever built. And well, in sheer bulk, it certainly does exceed the energies of our particle accelerators. But here's the kicker. The ionized particles generated by high voltages in the lightning can literally spray into the atmosphere, create ionized plasma. Some of them make blue jets of light glowing in our atmosphere, and some make red sprites, as they're called, that can be seen from space. The most amazing thing about these is the energies are so high that the top of the atmosphere where the lightning bolts are flying actually emits bursts of gamma radiation. Now, there were very few known natural sources of gamma radiation that were on the books, and people didn't even expect this. We often see bursts of gamma radiation from space, and we're not really sure where it comes from. In many cases, it can be very difficult to localize them because we don't have a lot of lenses that can focus gamma rays into an image. There is a way to do it, however. As you would expect, gamma rays will pass right through a normal lens. But people are clever, and by changing the index of refraction of materials, by using layers of lead and aluminum of varying wedge thicknesses, they're able to actually make X-ray and gamma ray optics that will focus it to a degree. But even better, by using what's known as Gray's angle optics, they make a curved conic form with a metallic coating on the inside, and the gamma rays cutting in bounce off the edge. They graze the edge of the interior of the telescope's cone and come down to an imager. Gray's angle optics can focus gamma rays effectively enough that we can get a rough idea of where the sources are. Some of them appear to be coming from the atmospheres of gas giant planets like Jupiter. Others appear to be coming from stellar phenomena like black hole collisions, neutron stars, eruptions in solar photospheres, the glowing gas around the exterior of a star. So we're getting pretty well informed about gamma ray sources. It's really amazing that we get a wild card out of the blue and find out that our own atmosphere is generating bursts of them during every thunderstorm. So it's amazing what you can discover when you apply a little technology to it. And by the way, one of the most interesting effects in aerology is something known as, okay, when gases expand, they cool. When they expand rapidly, they cool a lot. This is called the Joule-Thomson effect. And so in 1852, these two scientists came up with a name for this. They would take compressed gases, they'd let them escape from a vessel, and it would get cold. And this is, of course, the birth of the idea of refrigeration. But there's another thing that happens in nature. Imagine a large, moisture-laden mass of warm air moving along the ground and then running up to the edge of a mountain range. It crunches up against the mountain range, it heats the air momentarily in compression, and then it spurts up into the sky, decompresses, and freezes. Now, not the air, but the moisture. And this is why the rain and snow fall on the outside edge of a range of mountains, and past a mountain range on the interior of a continent, you usually have a desert. The Joule-Thomson effect from masses of moving air that are under compression and then released cause all the rain, all the precipitation on the outside toward the sea, and almost nothing reaches the interior. And this is why deserts are always behind a barrier wall of mountains. The moisture actually precipitates out on the mountain slope. So interesting how our physics becomes capable of explaining some of the things that happen in our weather that way. Well, anyway, aerology, the study of weather, not just down here, the study of the atmosphere all the way to the top. And I hope that you've heard some interesting things today, and it's given you something to think about. And it shows sort of some of the connections between all of the fields of knowledge that we've been accumulating for so many thousands of years. The study of the air can be a fascinating thing. And to think that the hot air balloon that was invented actually became an element of predicting the weather and understanding our atmosphere. And incidentally, a lot of people don't know it, there actually was an Air Force during the Civil War in the United States. The Air Force consisted of balloons, and many of them were tethered and used to detect movements of enemies, and messages could be shot down the line in a bottle with a wire. So you could get up into the air, scout the territory, write down a message, slide it down the wire, and you were in the Air Force in the 1800s. Well, I hope this has been a fascinating exploration of aerology, and I am going to open the floor for comments and questions. And meanwhile, I'm going to encourage you to go to the Universe Science Center or SchultzLaboratories.com, sign up for our classes, sign up as a member, support our growth and the addition of new materials and exhibits to our galleries. And if you're an educator and you want to share what you know, we can set you up with a place to display your works, some sort of a gallery, and we can set you up with a classroom so that you can teach people all over the world. So contact us, and we will be very happy to work with you on that. Well, I don't see any questions or comments. So at this point, I'm going to, hold on, let me back up a little bit. Is biology a part of serology? Actually, I would say it's the other way around. Biology, as most people understand, is the study of life in its broadest sense. And I would not think that something that depends on an aspect of life would be the greater discipline. And maybe I have that wrong, but biology is the study of life itself. When we talk about disciplines being a subset of other disciplines, serology, you're really looking at blood serum, and in order for that to work, you have to have a living organism. So serology would be a subset of biology, particularly in the medical fields. And that's just my opinion, but I believe that that would be true. So I hope that's a helpful answer. And okay, well, I'm going to read my quote for the day, and it is, "And do not grieve the Holy Spirit of God, by whom you were sealed for the day of redemption." And that's Ephesians 4:30. So, what a wonderful world we live in, and I am very happy to have these chats, and I hope to entertain more questions and share a little bit of what I've learned, and hopefully make some things clear that might not be understandable in the world. I love to share what I know, and I love to hear what other people have to share as well. So be sure to come on and join us live on the Randomizer whenever you can. Meanwhile, I'm going to say have a wonderful day and make the world a better place. I'm Charles Schultz with the Randomizer, and we'll see you next time.